Good afternoon in Shanghai and good morning in Switzerland. Welcome to join our first Art Science Dialogues webinar. My name is Sisi. I'm the head of Art Science at Swissnex China. Before we start, I'd like to give a brief introduction of our organization. Swissnex China is the initiative of the Swiss State Secretariat for Education, Research and Innovation. Around the world, we have 5 offices, 2 in the States, 1 in India, 1 in Brazil, and us in China. For the past 11 years, we have been actively connecting the dots between China and Switzerland in science, higher education, and innovation. The Art Science Dialogues you're attending today is a brand new webinar series. It will take place once a month from May to August via Zoom, covering topics of design and material science, sonic art and neuroscience, photography and environmental ecology, and new interdisciplinary initiatives. Through this series, we will try to present artistic projects with strong scientific and research background, and also introduce new initiatives from Swiss academia. So today is our first lecture of the Art Science Dialogues, and we chose the topic of design and material science. We believe good design combines science and art in creative ways, and the breakthroughs in material science are very likely to affect the future of design greatly. Therefore, we have invited Ms. Gabrielle Dobenecker, Head Fundraising, Entrepreneurship and Industry Relations at EMPA, the Swiss Federal Laboratories for Material Science and Technology, and also Ms. Lila Wu, founder at Uni Group, to lead our journey into design and material science. So we will have 2 presentations followed by a discussion and Q&A session. So for our audience, you may use the Q&A tab on the bottom to type in the questions, and we will answer the questions at the end of our webinar. Okay, let's welcome Gabrielle for the first presentation.
Yes, good afternoon to all of you, and again, good morning to those who are based in Europe. I'm very happy to give you in the next 15 minutes an overview about EMPA and some of its activities in material research and developing, as well as the relation with from research to material design and later on material processing. Next. Next slide, please. Yes, next slide, please. At EMPA, as Sissy already said, we are the Federal Research Institute for Material Science and Technology and part of the ETH domain in Switzerland. And our main goal is conducting cutting-edge material and technology research. Researching new materials and driving forward innovative technologies, providing impetus for sustainable development of our society, creating scientific basics for political and social decision. These are our central goals, which we pursue through research and development with a lot of cooperation and partnerships within academia, but especially also with industrial partners. We are focused on meeting requirements of industry and society as well, and try to challenge face the challenges that we have today in the world, and even maybe more so the years to come. The first one comes to our mind is definitely a sustainable and safe security energy supply. Another one is global climate, the environment, and our dwindling natural resources, beside fossil fuels. Not to forget the renewal of our built infrastructure, that is building streets, bridges, tunnels, many of which are getting a bit long in the tooth. And closer to home, of course, personal health and well-being, an issue that is becoming ever more important in the light of our increasing life expectancy. EMPA is trying to provide answers and solutions, new ideas and impulses by concentrating our R&D activities within 5 research-focused areas, as you see at the bottom of the slide. At the core, our objectives remain unchanged: materials and technology for a livable future. Because meeting today's challenges requires, above all, innovative materials and sustainable technology. Next. Here are some facts and figures just to give you a bit of an overview how big we are and what we're doing. We have over 1,000 employees, more half of them are scientists, organized in 6 departments with 33 labs at 3 sites here in Switzerland. Since one of our main goal is scientific excellence, is one of our main strengths also, we publish more than 1 reviewed ISI publication per scientist per year. Our budget in 2019 was over 170 million Swiss francs, which is roughly 170 million US dollars, 2/3 directly from our federal government and 1/3 acquired through third-party projects. Many of them from EU-funded projects, the Swiss National Science Foundation and the InnoSwiss. Next. Next. At any given time, about 300 research projects are running in various areas in parallel at EMPA. Here are just some examples of these. A big proportion of these are conducted with industrial partners, from small to medium-sized company to big corporation, nationally and internationally. In most of those projects, the research and development of new or improved materials or processes are the goal that we want to reach. Next. New materials have always been the prerequisite for qualified technology progresses for economic or social benefit. The physical properties of the material depend not only on its chemical composition, but also on its structural composition, so-called its architecture. This is especially important in the interplay between phases in the chemical composition and the interfaces in the architecture. And the smaller the structures of the material gets, the more important those interfaces become. Today, nanostructured materials are the approach that promise the most success in developing new materials with improved or even novel properties. The advance into the nanocosmos opens up fundamentally new approaches in materials research and development, and is often based on computational methods to the limits of what is physical possible. 1 nanometer, that is a billionth of a meter, or the length of 6 carbon bonds, is the scale on which modern materials science searches for new physical effects and aims to understand, influence, and improve the properties of materials in greater detail. Research in the nanometer range ultimately means working with atomic precision. If a material is defined as a material that can be processed for specific application, only suitable process and manufacturing technologies can turn a good material into a valuable material. And that comes also in place where the design process of the material, the processing later on, and the design of the application is very closely interlinked, even more so in the future. And this applies particularly to nanomaterials, which often have very limited process windows due to their complexity and manufacturing tolerances. It is therefore essential for the research and development of nanomaterials to take into account aspects of process engineering. Next. I now want to give you a number of concrete examples where design and development processes were key to create new exciting applications. On our way through those examples, we will be moving down from the macro to the micro and finally to the nano level. NEST is a modular research and innovation building on our EMPA campus in Düsseldorf that you might have seen or might have heard about. At NEST, new technologies, materials, and systems are tested, researched, and further developed and validated under real conditions and so-called units. These units are used either lived in or used as offices or meeting rooms. So there is also a close interaction between the new technologies applied and the final human users who use those habitats. Close cooperation with partners from research and industry ensures that innovative construction and energy technologies are put onto the market faster. The example I give you here, DFAB House, is one of those units. Is a residential units where about 3 visiting scientists are living. that has been digitally planned, but also predominantly digitally built using robots and 3D printing. And that was mainly developed by ETH in Zurich. One of the examples, next please, in that house is the smart slab ceiling that you see here at the top of the picture. The geometry of that smart slab ceiling is structurally optimized for a challenging load case involving cantilevers up to 4.5 meters. The material, a new ultra high performance fiber reinforced concrete, is distributed in a hierarchical grid of cursed ribs, as you can see in the picture. The 1.5 centimeter thick concrete fields between those ribs are doomed to maximize stability and to minimize the amount of material needed. Consequently, the slab only weighs 15 tons, which is almost 70% less in comparison to conventional solid concrete slabs. Only the combination here of a new material, this ultra high performance fiber reinforced concrete, a new design, and a new processing process made this possible. Next. Now we're coming to a very interesting class of materials. They're called metamaterials. I'm not sure if you're aware of them, so I'll give you a little bit of an introduction. A metamaterial is any material engineered to have a property that is not found in the naturally occurring material. They are made from assemblies of multiple elements fashioned from composite materials such as metal and plastics. Phononic crystals are a type of those metamaterials. They are synthetic materials that are formed by periodic variation of acoustic properties of the material. One of the main properties of phononic crystals is the possibility of having a so-called phononic bandgap. A phononic crystal with a phononic bandgap prevents phonon, that means the carriers of sound waves, of selected ranges of frequency from being transmitted through the material. A team at EMPA from our acoustic researchers lab has built those macroscopic crystals, as you see them in the picture. They are quite big in the macroscopic range that use internal rotation to tone down the propagation of waves. The method makes it possible to build very light and stiff materials that can swallow low frequencies very well. We call that, in that example, that we built a so-called cryptographic window. They built a window from 2 plexiglass plates with rotating discs integrated. The size of these discs is tuned to the frequency of the human speech. The idea is when certain frequencies are filtered out of speech, the spoken content becomes incomprehensible to the listener. You see there, you have a window that you can look through, so you can see the people maybe in the conference room on the other side, but you're not able to hear what they are talking about. We expect that these transparent phononic crystals could be very interesting for architects or interior designers. The physical trick makes it possible to produce rigid building materials with a stable shape that insulate sound very well, and that can be up to 100 times lighter than other phononic insulating materials, which have normally the same aspect and are used today. And that not only applies to interior design and architecture, but also to engineering, aircraft construction, or lightweight automotive construction. The filtering out of interfering frequencies with lightweight designer insulating materials could soon play a major role. Next. Next. But we are not only dealing with man-made materials, we are also trying to improve nature at EMPA. We take naturally existing structured and wood-based resources and tailor interaction between renewable polymers, nanoparticle, and colloids. Our approach is to combine existing wood architectures with controlled assembly of extracted wood components into new sustainable high-performance material. One tool of specific interest to us is the use of fungi, of enzymes as living organisms or biologically active substances to modify the wood material properties. In the pictures, you see a number of examples where those techniques are applied. On the top, you have a nanocellulose for novel implants. Here, a 3D printed ear. One down is a flexible biocompatible nanocellulose sensors to be used also in medical applications. The twisted tower that you see on the right is wood that is functionalized to structure itself, to shape itself. On the two bottom pictures on the left, you see instruments. The violins are treated microwood, and they have improved acoustic properties so that new built violins could sound like old Stradivari's. And the last one on the bottom is a part of cello that is made from Swiss ebony, a product that is developed and commercialized by an EMPA spin-off called Swiss Wood Solution that uses Swiss maple as a alternative to ebony, but having the same properties because it's functionalized and treated, but it's sustainable and it's entirely legal to export and to sell. Next, please. Now we're moving a little bit down from the macro level to the micro level and giving you an example of how to highly efficiently print thin film solar cells. A thin film copper, indium, gallium, selenide solar cells. I will spare you the long name from now on. It's also called shortly CIGS. That converts sunlight into electronic power. It is manufactured on the micro level by depositing a thin layer of copper, indium, gallium, and selenium on a plastic backing, along with electrodes on the front and on the back to collect the current. Because the material strongly absorbs sunlight due to those stacking of the different materials, it is a much thinner film is required than with other semiconductor materials. Those thin film solar cells is especially attractive for all applications where high efficiency, modular flexibility, lightweight, and affordable cost are desirable, ranging from portable electronics for outdoor-indoor use, automotive, PV integrated products to space application. EMPA has developed a scalable deposition process for those CIGS thin film solar cells suitable for high-speed inline production on flexible polymer rolls, a process that can be described a little bit as printing a newspaper with different colors. The precise composition and interfaces of the various layers, as you see the picture on the right, is key to achieve world record efficiency that we have shown with those solar cells with 20.8% efficiency last year. The technology itself is scaled up and commercialized by an EMPA spin-off, Flison in Switzerland. Next. We are now down to the somehow magical nano level where physical properties are different than on the macro level and where we have to design materials with atomic precision. For some years now, graphene has been regarded as the material of the future with possible applications such as stretchable electrodes, supercapacitors, and for nanoelectronics. Transistors on the basis of graphene are considered to be the potential successors of the today silicon components currently in use in all our electronic devices. However, as graphene is a semi-metal, it lacks, in contrast to silicon, an electronic bandgap and therefore has no switching capability, which is essential for electronic applications. With a new bottom-up method, it is now possible to synthesize graphene ribbons of the thickness of a single atom that are 1 nanometer wide and up to 50 nanometer in length that have a defined zigzag form, which exhibits a defined electronic bandgap. So here it's interesting that it's not the material in terms of self, like the chemical composition, this is carbon, but the form, how the molecules are arranged, give the material its properties. So the zigzag form is defining the bandgap. In cooperation with colleagues from Max Planck Institute in Germany and the Lawrence Berkeley National Laboratory in the US, EMPA researchers have already been able to realize a first component, a nano transistor with an ultra-short channel length of 20 nanometers. This transistor can achieve a current density of up to 1 billion amperes per square. But there is more in that atomic area. Next, please. With our latest research result, we have shown that the simple material graphene in the form of nanoribbons is equally suitable not only for nanoelectronics, as shown on the slide before, but also for spintronics, where the spin of the electron is associated magnetic moments are used, and quantum computing, the new holy grail of computing. Especially because the latter perhaps once be possible at room temperature, which is today still unthinkable. The only modification that needs to be made to the graphene nanoribbons in order to make them fit for one of those three applications is the topology of the edges. An example, a purely geometric modification. Depending on the configuration of the edges, is it an armchair like in a right lower left of the picture, the zigzag that I've already talked about, or mixed form, the graphene nanoribbons are suitable for electronic, spintronic, or quantum computing components. Again, the material, it's carbon, but the form of the molecule structure of the ribbon defines its properties. But to know which form is needed, this is strongly supported today by predicting chemical reactions through machine learning with state-of-the-art AI methods such as deep neural networks. Next. And with that, I'm at the end of giving you a little bit of an overview to the thousands of different projects and ideas that are running at EMPA, showing you from the macro to the nano level that novel material development is strongly linked with design and processing, not only for the material itself, but also with regard to the desired application. So thank you much for your attention, and I'm looking forward to your questions later on. Thank you.
Okay, thank you, Gabrielle, for the great presentation. Now, let's welcome the second speaker, Lila Wu from Uni Group. Lila, please.
Oh, hello? Can you hear me? Hello? Yes. So, hello everyone. My name is Lila. It's a great pleasure to be here in a dialogue with Gabby. So I would like to introduce briefly who's Uni. So Uni is very different from EMPA, but at the same time, we're a bit similar, so we're doing a lot of things. So instead of having these thousands of scientists, we have thousands of materials samples in our library. So we have the first ever international new material library that's curated and carefully selected by our team. And we have this online and offline library hosted here in Shanghai. And we have our own makerspace, which is a little different from university makerspaces. Our makerspace is dedicated to designers and industry to help them to apply new material and understand fabrication, such as digital fabrication. And we also use this lab to connect with thousands of factories in China. So in our lab, we also connect with the industry with university students, designers, scientists, and we host monthly events to bring new ideas and communicate with the industry. So this is one event we hosted together with Prohibition in 2018 with Swiss graphic designers. So in our little universe, in the middle, we have always design, and we have a makerspace that focuses on fabrication. And we have a new material library that goes across the entire universe because that's like the core of our business. And we have UniDo, which is a program we connect with universities in China. We have our own shop, which is a retail shop, which is a platform for us to do commercialization for all our new ideas and prototypes. And Uni Partner is a program we created with factories in China, mostly manufacturers. So I think Gabby has introduced this afternoon a lot of advanced materials from EMPA. For Uni, new material is a little bit of a wider definition. So what is new material for Uni? For example, this 4D printing technology is actually based on the 3D printing technology, but the fourth dimension is actually time, and the key is actually material. So in this composite polymer, design and scientist team from MIT has used a water-absorbing agent and mixed it with the polymer. So the polymer, when it absorbs water, it contracts, and this material will assemble itself. So we can imagine this technology to be applied to areas where humans cannot reach. So last year, we conducted this residency program with the founding member of the self-assembly team, is a designer from Switzerland, Christophe Gouberin. He has done a residency program with Uni. Our key is to help him to understand the Chinese industry and possibility to help him to commercialize this 4D printing technology with Chinese companies. So another story is with also Switzerland. We have brought the Swiss banknote, the latest one, to China. This banknote is very special. Not only for the beautiful design, but also the new technology to use AR to prove the banknote is real. So in this banknote, there are over 20 interesting technologies, from the special paper, special ink, special printing technologies to the AR technology. And we have presented this banknote together with the Swiss National Bank in Design Shanghai last year for the first time. And many Swiss people hadn't even seen the banknote, and the Chinese audience also view it as a piece of material instead of money. So Uni not only brings in this latest information about material science to the Chinese market, we also does a lot of technology integration. For example, this perforated aluminum panel is based on some existing technology. We use parametric design tools such as like Grasshopper, that we turn a photograph into pixels. And we use perforation technology to rotate and cut the holes on the aluminum panel. So these are all existing material and technology. We just integrated them and turned them into a new material that can present, such as this sort of image of Shanghai at the Bund. The Bund is the key location in Shanghai that runs through the whole city. So it's a river going through the whole city. We're showing 10 interesting photograph of Shanghai city with this technology on the bund. And this technology right now is mass produced in a lot of metal making factories. So after talking about what we think is new material, we also use these materials for a lot of industries. For example, we work with Shanghai Shumomatics. So that's like the biggest Medicare company in China. And we also work with an American company, which is BD. They researched and produced this, what's it called, automatic system that stores and pick up medicine. So with this, what we call smart pharmacy system, originally you need a lot of storage and a lot of display in the pharmacy. Nowadays, you only need screens and all the storage will be hidden. So Nuni designed and uses different technology and material in this new age pharmacy, or what you call the future pharmacy for China. And this is like a pilot project, and we are now moving on to many like a franchise model with these two companies. We also work with a lot of automobile industry. Now, this is like for a French car company, Peugeot, but we also work with BMW, Mercedes, Geely, and many other Chinese electronic car company about car exterior and interior finishing, such as this one. We are using recycled newspaper to turn it into a decorative panel. We call it newspaper wood. And at the same time, we help to bridge new material with the industry. So last year, we also brought a Swiss bag brand called Question. And this brand utilized a new material called banana tex. This material is actually made in Taiwan, and the bag is made in Dongguan in the southern China. And the raw material comes from Philippines. And Nuni is representing this company in China. And hopefully we will bring this brand successfully to the Chinese market. And meanwhile, we also help a lot of Chinese company, material company, to get into the global market. For example, this material is made in Zhejiang province. It's a reflective textile that usually is used in security wear. And the price of the material in general is a bit low. And after we introduce this material into our new library, and our member Maison Magella has used this new material in their couture collection in 2018 Paris Fashion Show. And after they use this material, now this material has been widely used in fashion industry, in sportwear, in luxury industry. So the price of this material has gone up to 3 times. And they successfully export this material to America and Europe. So I think it's important for Nuni to tell the audience, not only the industry and designers, but general public about what is new material. So we work with a lot of museums, and we did and we curated and organized and designed about 40 exhibitions in the past 2 years. And this one is one of our most successful exhibition with the Shanghai Science and Technology Museum, which has lasted 3 months, and we received about 3 million visitors. So I think in general, we want to do more and more of this type of general public education. So that brought us to more university collaboration. We want to introduce new material to more designers. So I myself teach at Tongji University in Shanghai. Also, I'm an education consultant for Art Center College of Art in United States. Last year, we created this course called Materialize Shanghai, and we have sponsored 14 students from America to study in Shanghai for 4 months. And we connect these 14 students with about 30 factories in China. There are material suppliers, there are manufacturers. So these students have created products based on Chinese culture, based on their own interests, based on Chinese traditional craftsmanship and advanced engineering and technology in China. So they have created this selection of product. For example, this is an instrument case. It's a guqin case. Guqin is a traditional Chinese instrument. And the student himself plays this instrument. He wants to create this lightweight composite material guqin case for the market that can help, I think, the players to carry this instrument in a more comfortable way. And this student is from Korea. He wants to create a knife that help people to socialize easier, and a knife that creates a much more comfortable grip based on ergonomics. And he also wants to use the traditional Chinese craftsmanship called 百宝嵌, 百宝 inlay. So this craftsmanship comes from the imperial palace, used to be for the king or the emperor. So the old craftsman uses all the treasure stone inlay into this sort of paint craftsmanship. So this craftsmanship has already lost for many years, and in the entire China, there are only 30 craftsmen that can do this complete craftsmanship. So he wants to use this craftsmanship, but together with new material, for example, like a bamboo composite or other composite material, to create this hard and soft inlay in the modern consumer product like a knife. So this knife will be incubated by K11 Craft Foundation, which is a famous institution or NGO in China. So we're also doing a lot of community projects, such as coffee recycling project like this one. We have been running this community project with Nespresso and Nestle, and they have donated a lot of waste coffee ground to us, and we have conducted over 20 workshops in our neighborhood. And all of these material samples, you can see here, are made out of coffee ground and mixed with different type of either bioplastic or plastic, or like paper, ceramic, or even I think textile. And we also try to 3D print coffee ground, and we turn coffee ground and recycle aluminum from Nespresso into this sort of product, and we're going to put them into market next year. So at the end of my speech, I would like to talk a little bit about why I, as a designer, will be getting into this material thinking or material-driven platform business. Because I've been practicing as an architect for over 10 years. And I realized in the design industry, many times we started with a design idea and we started doing prototype, and then we select the material, and this product may be getting into mass production if we're lucky. But then in this process, there is a lot of problem, and a lot of time our idea or innovation will die in the middle. Like from design to prototyping, maybe because a lot of designers don't even know the manufacturing process. Also in China, designers do not really talk to factory directly. So a lot of time there are lack of tools and knowledge to do prototyping. That's why we created a lab to help designers to understand the process. But then during the process from prototype to mass production, a lot of time, because of budget, because of many other reasons, we will tend to use very cheap material or very common material. So new material never have the chance to enter our eye or the market. And because new material maybe is more expensive because of lack of money, this innovative product will be still using traditional material. Or during the process of fundraising, the R&D process will be too long. Maybe it takes 2 years, 3 years, or 4 years. And the original market will be gone already. Maybe this product will already be less attractive for the market. So we think nowadays designers or industry will what we call design thinking when they're designing or producing new product to the market. We think in this period of time, especially during the virus, we should really rethink about the way we consume, really think about the way we design and produce. And I think also think about the environment at large. Instead of thinking from the market need, we should also think about what is the resource around us, what is the current problem on Earth, what type of material we should choose so that we can make our life better and also make our Earth better. So yeah, to end my speech, I would like to tell people what we are doing is we try to bridge the gap between design and application. So we created this new material awards in China this year. We would like designer and also scientists really both to enter these awards. So these two people, they're not sitting at the two ends of the table. They should be sitting together to talk about the future of our innovation, design, creativity, and also the life we want to have in the future. So thank you. That's my speech.
Okay, thank you, Lila. So now I guess it's time for our discussion part. Yes, okay. So we've seen from both your presentations a lot of interesting materials, whether it's artificial or from nature. So how is the new material invented or was found? What is a typical process for a research process of a new material?
Maybe I start coming from the research side. There are actually normally two starting points in my experience. The one thing is that coming from the knowledge about properties that materials can have, either through enhancement, functionalization, or the combination of components that haven't been used together before, new materials or new properties of materials are derived, just from the researcher who has an idea thinking that should be possible. In a lot of cases though, since we're working with industry, we've been approached by companies that have a certain need for a material. I'll give you an example. We've been approached a couple of times before by companies from the Swiss watchmaking industry. That was Omega. They were looking for one of their very high class watches. They want to have had a red ceramic lunette. And before that, it was not possible to create bright red ceramics, and you cannot use like normal dyes because they're organic that we would use to dye any kind of reds that you friends like to have in textiles, because the sintering temperature is too high for any of those organic dyes. And you also had the requirement that you couldn't use toxic materials, and you had also requirements from industry that those lunettes are normally there are little indents in it where they put numbers in. They need to be not too brittle, so they could be processed in a usual way like watch lunettes are processed. And it took quite a while to find a material in the end, or a combination of material. It was possible to create these bright red ceramics for the first time in the world. Another way that sometimes happens with materials, but also with processes, that you have developed something with a certain application in mind, and then you realize that it could be also used in a very, very different application. Give you one example. We have a team that is very into measuring molecules in the atmosphere, measuring gas molecules in the atmosphere to trace down gases like ozone or others. And then came the idea, we cannot apply that to an industrial process, where normally aerosol cans, when they are tested against leakage, they are put into warm water and you see the bubbles coming out, and then you know there is a leakage can in the process, and you had to find it out, and that takes time and it takes a lot of energy because you need to heat up the water. With the quantum cascade laser that the team developed to trace molecules in air, you could also trace the aerosol molecules that come out of a leaking can. And so the process is now far cheaper, far faster, because there are like thousands of cans that pass that laser by in a minute, and the leaking can is detected by detecting the molecule, and then it's put out. And the next idea came talking to people from medicine, and said, if you can tune that laser so specifically to certain molecules, why can we use it for medical application, where you can, for instance, trace molecules, certain molecules, for instance, that are indicating stomach cancer in the breath of a patient. So you see, sometimes an idea, a material, a process is firstly, let's say, ideate for a certain application in mind, but can be used rather broadly. So for us, it's also quite important that the talk, and Leila already mentioned it, has to be very interdisciplinary, because a lot of people, they have so much experience in their area of expertise, but never have thought of applying that to other application areas. And I think there's a wealth of people talking together, as Leila mentioned, to bring out new ideas and new possibilities with existing material, but also bringing ideas from certain application to other applications, say, yeah, why can't we use that? Or why have you ever thought about doing that and that? So there is, let us say, there is a lot of space still to conquer.
Thank you. Yes. So are there any requests from the designers, since the designers are dealing a lot with the materials?
Oh yeah, that's a lot. Actually, most designers, I'm talking about fashion designer, graphic designers, architect, like almost every type of designers. They are all trained with, nowadays from computers. So they all started with like computer designing skill or hand drawing. So very few nowadays, they specialize in this material. So a lot of them actually studying to know material after they started working. In a way, their knowledge about material is very general, like wood, glass, metal. They don't really have like a very detailed idea about, self-healing concrete and how is that different from a concrete. So in general, I think there is a big gap between the knowledge of designers and the actual development of advanced materials. That's why I think nowadays we get thousands of requests from different type of designers daily for their different need and projects. And we're trying to process these projects by connecting them to the right material supply.
What we see here in Switzerland, that is maybe due to the fact that the country is small, only 8 million inhabitants, that is like a small to medium-sized city in China, that people are quite well connected, and that also the universities or universities of applied science that offer studies in design, in industrial design or product design, are now cooperating with us. We had projects with designers from this Züricher Hochschule der Künste, or with the Hochschule Luzern, who are in design. So it's starting out, but Laila is absolutely right. In the training, in the formation of designers, materials are looked at mostly only in the bachelor area, and then it's more like a look back in history of design and the basics. So what is there? And for me, it's understandably materials itself is such a broad area of research and expertise. And I guess even with us, with our 1,000 people, we have experts, for instance, in concrete, and they don't know much about textiles. So we have the challenge that we address to get into to them to talk interdisciplinary and transdisciplinary about properties, about applications, just to get something new started.
Also, we get approached by a lot of nowadays brands and factories about how to utilize their waste stream to turn them into a useful matter or useful material. So this is becoming more and more, I would say, popular in terms of material development. So a lot of requests come from the industry to utilize their waste.
Absolutely, and it's not what we. I think the term for it would be circular economy. It's not only that you look how sustainable a material in its production. That means how sustainable it is in terms of eco aspects, how to get it, how to produce it, but also can you reuse it, or can you reassemble things when they are not used anymore? Why don't you, for instance, need to buy a carpet, but you can rent a carpet when it's built in that way that the producer of the carpet takes it up from your home 5 years later and reassemble it in its fiber and reuse it for a new carpet.
Okay, thank you. So we have some questions from the audience coming in now. The first one is from Felix. This question is for Gabby.
Okay.
Objects such as the human ear. Why are objects with cellulose content important? Are additional future applications? So this is for Gabby.
Yeah. I think there are two reasons for it, because these nanocellulose material is a bioacceptable product in theory, or so of course, because it's a medical product, it has to go to those strict processes of having it certified. But generally, it is a natural material that is accepted by the human body. And so it gives, and it has properties about its structure and how to implement other materials into it, like gels and colloid, that makes it very attractive for replacement in human organs that need to have a certain structure. Because as you know, the ear, it's not in terms, it's an active organ like a liver, where the liver cells have a specific, but they need to have a certain structure, the ear, and it has to have a certain, I think, stiffness, but also it has to have a certain softness. And this can be obviously very well, let's say, recreated with those nanocellulose material. I hope that answers the question.
Thank you. So the next question comes from Grace Yu. The question is, is there a lot of wasting in our life and also the production of industrial production? So in the future, what kind of new material, which is more environmental friendly, is needed in the future? Thank you.
Maybe answer a little. I think it's really based on what type of waste, like in terms of quantity. And in general, I think when I read the paper from Chinese government, that I think China as the world factory, we have a lot of wastage in terms of water pollution. So nowadays, you see that Chinese government has built a lot of water treatment plants nationally to deal with this problem. And at the same time, China also has steel, a lot of metal production, also a lot of like I would say textile, metal, almost everything, paper, almost every material has a large quantity of production in China. I think the point is not what material, but rather how to turn the waste into something useful. Yeah.
And it's not only limited to materials, it's also limited to, let's say, how they are put together. We have in one of those nest units that where I showed you the DFAB house, it's called the UMA, it's the urban mining and recycling units, where you just shift the view how you look at a house or at an apartment, that it's not something that is destroyed, demolished in the end, whether it's not longer in use, but that it can be reassembled and can be looked at as an urban mine for important resources and materials. You now have a lot of materials these days that become scarce, that there is more in the usage already or on the waste bins than it is still in the earth. So it's not only a question of is it ecologically friendly, how to mine, for instance, a metal or so, but is there still enough there for the growing need of the world population? And it's there. But for instance, one of the examples where we really try to build that unit in a way that it can be reassembled, or let's say get out together and recycled, that you today have conventional processes. For instance, in bathroom, you will use silicone to glue things together to make that the water stop getting into it. You cannot use that if you want to get everything out again and sort the different materials that you use. So it's not just a question of the materials, this is also how products and systems are put together.
Cannot agree more.
Yeah. So we have another question for Gabby. It's from anonymous attendee. I've noticed there were PhD students working in EMPA. To my understanding, most of them were from an engineer technical background. I'm wondering if there is any chance for one from design background to enter EMPA.
Admittingly, that's right. So far, our PhDs have either a background in physics, in chemistry, in material science, and engineering, some of them in biology. So far, to my knowledge, of those nearly 200, there is no design student as of today, but that may change. And you also need to know that as EMPA, we are not a title-giving organization, so the students are normally, they're employed with us, they do their PhD work with us, but the title they are enlisted in one of Swiss or international universities. So we have 45 nations on our campus, so it's very international, and we have PhD students, postdocs from all over the world, including China.
Great.
Thank you. So I think both of you also mentioned about the design education and the gap between material science and also the designers. So how do you see this situation? Are there any improvements that we could do to bridge these two community and to help improving the situation?
I would like to say something first, because I think in general, it's quite difficult to put them into the core curriculum right now, like immediately into every design university or school about advanced material. Part of the reason is not every design discipline need to know everything. So it's more like who should define what should be communicated at the foundation year or level in the design education, and when, like whether it's first year, second year, you know, what and when. And the second part is, I think, about research, like what Gabby introduced, like an institution like EMPA has mostly scientists, but they closely work with design universities. So here in China, I think we are lack of this sort of bridge. Like we don't have, like we have 中科院, but we don't have this institution closely working with every design university, you know what I mean? And also for Tongji University, it's already the top, the ranking #1 in Asia, in China, and also number 13 in Asia in terms of design school ranking. But then still inside our faculty, we don't have a direct bridge with another material research institution and material faculty, you know, so that is a missing link here. And I think yeah, we definitely want to bridge it.
Yeah, and I think, and Lila, you with Nani, you're doing a fantastic work of creating a platform where people from different backgrounds, even the broad public, gets educated, but not only educated, also I think excited about new materials and its possibilities. Because I think with everything, it starts in the head of the people. If they are open-minded, if they are excited, if they know that there is something, they start researching and they start looking for new ideas and new networks and new people to meet and collaborate with.
Yes, that's also what we are doing actually at Swissnex China. So we try to bridge the community between art and science, and also between Switzerland and China. So I think we are slowly reaching our time limits. For the questions that are not answered, we will try to answer you by email. So we can show the last slide. So for our audience, you can reach us by sending us email at artscience@swissnexchina.org. And as mentioned at the beginning, this is our first Art Science Dialogues, and we are having the next one on 2nd of June on sonic arts and neuroscience. So please stay tuned with us for further updates. So we would like to see you in our next event. Thank you.
Thank you.
Thank you,
Thank you.
Gabby.
Thank you. Bye-bye. Thank you.
Bye-bye.